we're going to be talking about diazonium salts. So in this case, we're going to be taking an amine, treating it with a nitrite salt and an acid, making in situ nitrous acid, and we're going to end up making a diazonium species. And we're going to see that these are going to be terribly bad things to have on regular old alkyl chains, but they're really useful if they're on aromatic chains. So let's go ahead and take a look at what's happening here. So what we're going to do is see that this, turns into nitrous acid, right? Plus the chloride, I guess. And we're going to see that this thing will dehydrate just like the nitric acid did with our sulfuric acid before. We're going to see that... no, it's not plus. Just like before, we're going to end up protonating this thing. So we've protonated it once. We're going to go ahead and now protonate it again. Here's another HCl. And like before, we're going to kind of have same idea happening here. We're going to end up kicking this guy out there, and we're going to end up getting rid of our water. And we end up making a species just like the nitronium ion from before. This is the nitrinium ion. And that's going to be our reactive species here. So it's kind of just like before when we looked at nitration of benzene. We're going to have something similar here. And if we resonate this thing, we see we can get the positive onto nitrogen instead by plopping off the lone pair, or this triple bond to a lone pair. We'll have a positive charge on nitrogen instead. And that's typically the more common form because nitrogen is better at accommodating a positive charge than oxygen is because nitrogen is less electronegative. So let's see now that this is our reactive species here. And so we can go ahead and use it. So let's take an amine. Let's say we've got that propylamine here. We're going to take our reactive species. And we're going to go ahead and attack it. So we're going to go ahead and attack just like as if this was a carbonyl or something. I think so. We're going to go ahead and end up with this here. This guy's still positively charged, by the way. So now we're going to have our good friend water, which was produced in the dehydration of the nitrite. Come and act as a base. We have protonated species. We're going to deprotonate that. Like so. You can leave this as the N double bond O, but we'll see it'll be a little bit easier for us if we keep it separate because we're going to be protonating this thing. So here's another one. Actually, we can even use the acid we just made. H3O. No, sorry. H2OH. There we go. Let's go ahead and protonate that one. just a proton shift. We're moving a proton from the nitrogen to the oxygen. And we have the OH now. All right, guess what we're going to do? We are going to go ahead and now steal another proton away from one of our nitrogens, which is going to help stabilize this a little bit more. All this stuff is just protons moving around, honestly. That's the entire mechanism for this thing. So proton comes around. Actually, that's going to go ahead and we're going to go ahead and actually make a double bond there. We're not going to, because we're going to stabilize that nitrogen next to it. Minus another H3O plus. And now we're going to go ahead and protonate the oxygen again. Do you see how many protonations, deprotonations we've done? It's pretty crazy. Oops, too many lone pairs. So we're going to now have OH2 plus, keeping our lone pairs here out of the way. I should have chosen a shorter molecule, shouldn't I? All right, here we go. Now we can make this happen. Simply we close down this bit here, and we end up kicking out our water for like the 5th time. And now we have this dude. So, we have our diazonium. Hooray. Exciting stuff. So, it's a process of just proton transfer, proton transfer, proton transfer, proton transfer, proton transfer, and then finally our water leaves. And that's the entire mechanism. So, grabbing protons, moving them around. And so we end up with our diazonium species here. This is an incredibly strong leaving group. Perhaps one of the strongest ones there is. So much so because it produces nitrogen gas when it leaves. And as we know, when we have gaseous products, they just float away. Le Chatelier's principle pushes the reaction to the right, and so you just keep losing them. And so we're going to see that just alkyl ones are unstable, because what happens is you just lose N2, it just leaves. And now you're left with a carbocation. You lose nitrogen gas, and now you're left with this primary carbocation, which is just terribly unstable. And it's going to go and migrate to, the secondary position, but what's it going to do then? Who knows, right? I guess it'll react with your counterion, depending on what your counterion is for the diazonium. In this case, it's probably chloride, but they're terribly unstable because they're such a good leaving group. As a result, we don't typically see these used as in alkyl substrates, but we do see them used in aromatic ones. We're going to see that aromatic diazonium they are stable enough to react. And we're going to have a whole group of reactions for this, which thankfully we're not going to need to know mechanisms for. So we're going to get a whole array of what are called Sandman reactions, after, of course, the scientists who did this. So we're going to be taking and doing a lot of stuff with it. So we can use all manner of copper salts to do this. These are copper 1 salts, by the way, and you'll end up just substituting in your whatever is on your position. Look, another way to put a CN on, since apparently some of y'all forgot how to do that. But I guess we'll see that during the weekend. All right, so these are all copper salts that you can use, that you can install one of these on your diazonium. Diazonium by itself, by the way, is a strong deactivator, just for purposes. If you happen to have that and if you want to do some aromatic reactions on it, just be aware that the diazonium species is a strong deactivator. So nitrate, when you put it on, when you nitrate your benzene, it's a strong deactivator. You reduce it to the amine, that's a strong activator. And then you can convert it to diazonium, which is now a strong deactivator. So you can mess with this quite a bit. So we're adding more to your toolkit so that you can't forget your aromatic reactions, because they're going to come back to haunt you on exam 3. Hooray. So we'll get there. A couple other things you can do with this. Perhaps the most useful, if you treat this with phosphorus acid, you just get rid of it. I guess we can say there's an H here now. That would be one way to describe that. But this is now a way that you can nitrate something, make an amine there, use that as a directing group or to activate your ring, turn it into a diazonium, treat it with phosphorus acid, and now it's gone. So just like with sulfonation and desulfonation, you can remove them. This is a way to remove a nitrogen-containing species. So we can convert it to a diazonium salt using sodium nitrite and HCl, and then from there we can do all sorts of fun stuff. Let's see. We can use this little dude to put fluorine on, if we were so inclined. So fluorine we could put on with NaS, but this would be a way to do it if we didn't have a different leaving group or something, or the incorrect place of putting. Remember, to do NaS, you need a ortho or para strong withdrawing group. With these reactions, they're substituting directly on where the diazonium is. So you don't need anything else on your ring. Your other things on the ring shouldn't interfere with this anyway. So it's a great way to install it at a particular position without having to worry about having other groups to direct things. Let's see, what else can we do with this? Those are kind of the main ones. So, biggest one probably this guy, most useful to remove it, honestly. But we can do all sorts of fun things with these Sandman reagents. Let's see, we can also we can couple these things together if we were so inclined. It's a little bit less common to do this, but you can make a Diazo reagent by coupling your diazonium salt with another one. If you take an aryl diazonium species, oops, the plus there, and if you put it with another aromatic, with some sort of activating group, you will end up coupling them together, which is pretty interesting. So let's say we're going to add this dude. Well, OH is an activating group, strong activator, right? What's going to happen is you're going to actually get these two to couple together. And so you can couple things together as well. So you can use this to attach other benzenes, substituted benzenes onto your diazonium. And these are going to be called azo species. Which are often very colorful. And so you see many of these things used as dyes or indicators because they're pretty colorful. So that's kind of their utility. Synthetically, like it's kind of hard to use them otherwise, but like they're a product of themselves. So in and of themselves. So you can use the azo compounds for your various dyeing your shirts red, as is the case today for me. So fun stuff we can do with them. So that's kind of just the last little bit of our amine journey. So this is now taking the amines idea and the aromatic idea, putting them together. And so we now have 6 more reactions we can do with amine-based aromatics. So, yeah, go ahead. SD, strong deactivator. So, yeah, if you wanted to do a different reaction on this, it would be a meta director, blah, 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 all that fun stuff. So it would treat it like any other strong deactivator, nitro group, whatever. So, cool. All right. So, any other questions on the diazonium stuff? Or on the... Actually, that was all. Okay, cool. Let's start our next bit then. We're going to talk about carboxylic acids and derivatives. So this is 2 chapters in the book. Derivatives. No, let's try that again. Derivatives. This one, 2 chapters in the book, but we're going to kind of just combine them because they are really the same idea. And we're going to see all the reactions that we're going to cover basically follow the exact same mechanism. So it's a nice set of things. There's a lot of reactions that we can do, converting carboxylic acids into various derivatives. Let's talk about all the various functional groups here we're going to talk about. So we have actually 6 things that we're going to be talking about. 6 different functional groups that are going to be covered in this chapter. So first one, of course, is the carboxylic acid itself. Also going to be talking about esters, anhydrides, alkyl halides, amides, and nitriles. So all of these are considered carboxylic acid derivatives, the 5 on the right here. And so carboxylic acid is kind of the main subject, I suppose, though we're going to see that alkyl halides are the most synthetically useful. And amides, on the other hand, are probably the least useful. And so we're going to be focusing first a little bit on carboxylic acids. We'll talk about nomenclature as well. And we will then talk about alkyl halides, and we're going to see that and we're going to talk about each of these groups really. So lots of reactions, but we're going to see they're all essentially the same. So it just depends. We're going to see that alkyl halides will just be the most reactive, then anhydrides will be, then esters, then the acids themselves, then the amides, and nitriles do their own thing. So carboxylic acid. Yeah, go ahead. Yes, it certainly will, but that's later on. So, and we'll talk about that kind of when we summarize. So we'll be talking about them in order of reactivity. So we're going to start with alkyl halides after we just do some basic carboxylic acid stuff. So just so you know, these are kind of defined by having a carbon connected to 3 heteroatoms. So, or 3 bonds, 2 heteroatoms, I should say. So in the carboxylic acid, you have 2 bonds as a carbonyl and 1 bond to the OH. So 3 nitriles the same way. You have 3 bonds to nitrogen. Alkyl halides, 2 bonds to oxygen, 1 bond to a halogen. So good stuff. All right, let's talk about carboxylic acids. So as we know, carboxylic acids are named as such because they are acidic. Very exciting. So amines are basic, right? Carboxylic acids, on the other hand, are acidic. We're going to see that this is a pKa of 4 to 5, thereabouts. Acetic acid, a pKa of 4.74. You know, pretty standard, standard one. So we're looking at around 4 or 5 for pKa's here. So they're weak acids. And of course, as we know, we can mess with these by adding various groups to it. We see that the reason that these are stabilized, by the way, of course, is due to resonance. So your base that comes out and resonate 105 stuff here. So you can resonate. And that's the reason that these are 10 to the 10 times more acidic than plain old alcohols, is because of this resonance. So it's an extremely strong effect. And typically we're going to see that other nearby groups can alter the acidity. So for example, if we have, let's say we've got chloroacetic acid. This one's got a pKa of like, I don't know, 2.9 or so, if I remember correctly. If you put another chlorine on there, then we're going down to like 2-ish. And a third chlorine, we're going to like 1.5, thereabouts, rough numbers. But we see here that the more chlorines, more halogens we put on nearby our acid, we're going to end up lowering its pKa. So we're going to stabilize it, inductively speaking. So not only do we have resonance that's helped stabilizing that negative charge, but we're also not going to be pulling electron density away towards the chlorines, which is going to help further stabilize it. Of course, stuff has to be nearby. So something like this, the chlorine way over here, not going to help you out. We're going to see that this one will still have a pKa of 4 to 5. If you have donating groups, on the other hand, if you have an electron donating group, say a T-butyl group, roughly donating. This pKa will be, 5-ish. So a little bit higher. Acetic acid pK is 4.74. This one might be like 4.9, might be 5. It's very slightly higher. Because having an electron donating group next to your acid is going to donate electron density towards it, which is what you don't want. Your conjugate base is trying to resonate that lone pair, that negative charge, that electron density. And so by putting more into the system, you're making it worse. And we see that this is kind of the case with aromatics as well. We're going to see that, nitro groups and all that will help stabilize things. So electron withdrawing groups make these more acidic. And donating groups make them less acidic. All right, so one, I suppose, important one would be an amino acid. Alanine, maybe. Remember that amines are... Do we have a question? No? Okay. Amines are typically protonated at physiological pH. And we're going to see that because of that, we have now a nice, strong electron withdrawing group right next to our carboxylic acid. The pK of this one drops to about 2.5. So it drastically lowers your pKa. So in physiological conditions, you'll often see these as carboxylates. So you have, in amino acids, you have positively charged amines and negatively charged carboxylic acid groups, just because of the conditions nearby. So because the nitrogen bit there is electron withdrawing, it's going to help stabilize your carboxylate. On the other hand, your carboxylate will help stabilize your amine, so they both help each other out. It makes the amine more basic, and it makes the carboxylic acid more acidic. So it works both ways there. Cool. So that's just some acidity stuff. So that's kind of a review, right? Talk about nomenclature. Y'all thought we were done with nomenclature. All right. We have a couple of common acids that you should probably know. This is acetic acid. Hopefully that one is well known to you. Propionic acid and butyric acid. These are common names for acids. These are commonly used ones. These are common names. These are not IUPAC names, but they are accepted by IUPAC as common names. So make sure you know these ones. Okay, if we were to name them in IUPAC, like standard systematic naming, we would say that this one, why did I draw it again? This one is ethanoic acid. This one is propanoic acid. And butanoic acid. We're going to see that we take the name, butane, propane, ethane, we get rid of the E, and we add oic acid. So we take our kind of alkyl substituent, oic acid. That's the standard way. So pentanoic acid, hexanoic acid, octanoic acid, whatever it may be. We're going to see that there is not going to be, well, all right, we're going to see this is the parent name, right? it is very unlikely that you will have a substituent carboxylic acid because carboxylic acids are priority number 1 in naming things. They have the highest priority functional group for nomenclature purposes. And so it is unlikely to see them as a prefix, but I'll tell you that prefix anyway, it's carboxy. And you would really only ever see carboxy as a substituent. Carboxy would be something like acetoxy. These are only if you have like multiple carboxylic acids in your structure and there's no way to get them all in the same chain. So it's not common at all to see them as a prefix, but if you see something like an acetoxy group, that is a carboxylic acid. All right? It's unlikely. So just like, you know, our normal ways of naming things, well, we'll have all that. I'm going to switch screens for just a second because I want to bring us way back to the nomenclature thing. So, yeah, go ahead. Yeah. Is systematic name, yeah. All right, so we're going to switch over to this thing here real quick, wherever it went. Where did it go? Here it is. Okay, so this is, because we're going to have all these functional groups, I just want to put all of it out. Oh my God, go away. Right at the start. So carboxylic acids are always going to be our highest priority. You can't? Classic. Okay, let's try this again. All right. Okay, this one should work. Yes, good. Ta-da, I see it. Okay, cool. So let me hop over there. Okay, so we see here, this table, it's in our extra resources at the very, very top of that channel. It has all of these. So it is unlikely that you're ever going to see carboxylic acids as prefixes, but here is their name, carboxy. And go ahead. Oh, okay. I can lower the quality. That might help. Okay. Okay. No. We'll get this to work. This is what we're going to do. I'm going to lower this to 720. No, I don't want to do that. I'll lower it to 15 FPS. That might help. Okay. Also, Audrey, if you want, here, I'll link what I'm showing here. Wow, if my mouse will behave. Okay, it won't, but okay. I'm gonna just copy this Audrey here. Oops. Okay, so that's what we're looking at right now. So, so you can go ahead and open that up. So, carboxy. This is the prefix for carboxylic acid. It's not something that we're going to see very often. So, ethanoxy would be something like that you might see, or acetoxy. Not very common. The suffix name for it would be oxoic acid. We're going to see if we have a cyclic alkane like cyclohexane, we would say cyclohexane carboxylic acid, which is a whole mouthful. A little bit less common that way, but that is technically the name. So we'll write all this down. But I just want to show you all of these kind of all at once, as well as this handy chart so you can use it. Sulfonic acids we don't really talk about as a functional group, so we'll skip down to esters. So esters will be, for all intents and purposes, priority 2 for us. Their prefix name would be alkoxycarbonyl. So in this example, methoxycarbonyl is here on the right of this grayish molecule, and then acetic acid will be the parent structure. So the carbon that's part of the ester, as well as the carbon on the other side of the ester, those are both included in the ester prefix name. All right, so that's why this is known as acetic acid as the parent, even though there's 3 carbons in the structure, plus the 1 more carbon on the right side of the oxygen. So just keep that in mind. These are OAtes, so methyl ethanoate, methyl benzoate. You'd have, well, we'll go into this a little bit more specifically. You'd name the stuff that's next to the oxygen, and then the stuff next to the carbonyl. With acid halides, you'd say chlorocarbonyl or bromocarbonyl, or you'd say benzoyl chloride, benzoyl bromide, ethanoyl chloride, whatever it may be. So the prefix there, or the suffix there, is oil chloride or oil bromide. Those are typically the 2 that we see. We don't really see fluoride or iodide very much. Amides, we would say carbamoyl if we have a cyclic one, or we'd say aminocarbonyl. These are, for cyclic ones, carboxamide. For linear ones, amides. And then we would say, if there's stuff on the nitrogen, we would say N. We would name it like an amine, right? We'd say like N-ethyl, or like our favorite solvent, N,N-dimethylformamide. That's an amide. And it's based on formic acid, so we might say methanamide there if we wanted to be systematic. And then the last one we'll have is nitrile. The prefix there is cyano, and the suffix is nitrile. So these all of these derivatives and the carboxylic acids come before aldehydes and ketones. We've already seen aldehydes, ketones, then alcohols, ethiols, and then we go back to just plain old alkynes, or alkanes and all that. So these are the new ones. So carboxylic acid, ester, acid halide, amide, and nitrile. So 5 new groups we're going to have. And anhydrides isn't on here because they're not typically used because they're so reactive, but we'll have them as well. Okay, so let me switch back to our normal screen. Hopefully this won't mess things up. Right. Okay, are we back to our normal screen here?
Yes.
Cool. All right, so let's take a look at some examples. So, wow, did I just do that? No, no one saw that. That's good. Perfect. Okay, so, oops, the screen recorder is recording nothing. There we go. So this one, remember that cyclic ones, where your parent is a cyclic structure, they can have weirder names. This one would be cyclobutane carboxylic acid. So, whereas something like, let's say that's 5 carbons, this is just pentanoic acid. With cyclic ones, you have to say carboxylic acid just stuck onto your cyclic alkane name. So it's terrible, I know, but that's how we have to name these things. So, but plain old pentanoic acid. This one we would say, I guess will be consistent, pent for enoic acid. Again, your carboxylic acid typically will be priority 1, just like your aldehydes were, because carboxylic acids have to be terminal. You can't have an internal carboxylic acid because the carboxylic acid has 3 defined bonds. So it has to be at the terminus of something. So notice we have pentenoic acid this time because we have an alkene. Or if we had an alkyne, I think 1, 2, 3, 4, 5, 6. This time we have hex 5 ine oic acid. So it's just like how we would name other things. If we have alkenes, we change our parent name to ene. If we have alkynes, we change it to ine. If we have both, we would say this is, let's see, 1, 2, 3, hex 3 ene 5 ine oic acid. So just like before, we'd have all our stereochemistry, all of our locator numbers, everything that we would normally need for having multiple functional groups in a molecule. All that comes together here. So normally most carboxylic acids will end with oic acid. Cyclic alkanes that have carboxylic acid have carboxylic acid as their functional name. A little bit less common to see those, but that's what we'll have here. So let's see what else can we throw on. That's good for carboxylic acids like basic. We'll have more later, but we have other functional groups to do. So skipping over sulfonic acids, we're going to talk about esters now. So in ester, you name the part on the oxygen first, then you name the stuff next to the carbonyl second, and then this part here, it becomes O8. So with something like this, you would name this as isopropyl, because that's what we have here. We have an isopropyl group on the oxygen side of our ester. Oh, I should write esters. On the other side, we have, what is it, a sec-butyl? So we have a sec-butyl group. Oh, shame on me, I have some stereochemistry. Ho, ho, ho. Thought we were done. So no, 1, 2, 3, this is an S stereocenter. So isopropyl, still name that part first. Then we have a space, and then we would say 1, 2, actually this will be 1 S methyl propyl. Actually, we don't need parentheses here. 1S1 methylpropyl propanoate, sorry. This is butanoate. Why didn't nobody tell me? I don't know how to count. Butanoate. We have 1, 2, 3, 4 carbons here, and then we have the methyl group on carbon 2 because I don't know how to count. So sorry about that. Let's fix all these numbers. Isopropyl 2S 2-methylbutanoate. So isopropyl is the oxygen side of our ester. On the other side of our ester, we have an S stereocenter at carbon 2. Carbon 1 is the carbonyl carbon itself. 1, 2, 3, 4. So that's why it's butanoate. And then we have on carbon 2 an S configured methyl group. Let's do some more. Go ahead. So we always will name the oxygen side first, and then the carbonyl side. So first we're going to name our side, purple side. That of course is benzyl, right? Benzyl. 2,2-dichloro. Oops. What do we have here? Ethanoate. So whatever you have on the left, put it, or not the left, on the oxygen side, which is the left this time, keep that as its own name, space, the other half of the molecule, ending with or O8 at the end. If you want to make this super complicated, because we like to do that in OChem, we could do all this fun stuff, have some stereochemistry in there. If we're going to name the oxygen side, we're going to want a number closest to our oxygen, because that's what we're looking at here. So 1, 2, 3. So we don't go with the biggest chain, we go with carbon 1 is the one on the oxygen. And so we're always going to start there. And in this case, we have a methyl group without stereochemistry. Shame on me. Here, let's make them all wedges. That's going to be fun. So we've got a methyl group on carbon 1. We've got a chloro on carbon 2. If we look at the priorities here, I should use a different color. This is an S stereocenter. 1, 2, 3. This is an R stereocenter. And let's just do the other one while we're at it. This is S. Okay. So we would name this thing, I'm going to actually scroll down a little bit. We have to name the oxygen side first. And we would name this just as if it were an alkane. So we're going to put the chloro first, even though it's the farther number. We would say 1S, 2R, 2-chloro, 1-methyl. Space. Now we have the other half of the molecule. Carbon 1 is our carbonyl. 1, 2, 3, 4, 5. We have on carbon 2, that is an S stereocenter. 2-hydroxy pentanoate. So you would name these things just as if they were separate things, and then you just throw them together and stick the O8 at the end. Sometimes you'll see stuff with primes and stuff, and it just gets complicated, but we won't worry about that too much. Alrighty. What was that? That was esters. What's next? Acid halides. Oh, those are easy. All right. Questions on that one? Awesome. You love nomenclature, don't you? Should we just have nomenclature and that's it on our exam? That'd be fun. No, no dash there. There should be no space either, but as always, I've run out of room. Here, I can fix that by just dragging it down. Oh. We've lost a Y. So it would be like that. Yeah. Alrighty. So benzoic acid, right? This is benzoyl bromide. You've probably heard benzoyl peroxide before. That would be an acne curing medication, probably on every like other commercial, I feel like. But that's how you name a peroxy acid. But for naming acid halides, it's the same as acids, but um, we have the ending of oil, OYL, and then whatever your halogen is. So this is bromide. If it were a chloride instead, this would be benzoyl chloride. And so these would be our third priority group. These are acid halides, priority 3. If we were to just take this crazy thing here, stick a chloride on it, it would be exactly the same name. Magic of this. Let's make it into a chloride. Chloride is probably most common, more common than bromide is. We would name this exactly the same way we did before. BE. What was this? 1, 2, 3. 3. Oh my god, what am I saying? 1, 2, 3, 6. Hex. 3. Ene. 5. Ein. And then again, I've run out of room. Oil. Oh, we're good. Chloride. Because these are two separate words. So the oil part is separate from chloride. So we have a space there. So hex 3-ene 5-ine oil chloride. That would be how we would name this thing. Yeah, it's a transalkene, right? So we have with alkenes, when we're naming them, we look at what's the highest priority group on each side of the alkene. So on the left side of the alkene, this is our higher priority group because we go by atomic number, so carbon beats hydrogen out. On the other side, this is our higher priority group on the other side of the double bond, comparing that versus H. So that's going to win. Remember that if you have the trans, that's going to be an E alkene. If they were cis to each other, that would be a Z. So the Z one for this would look like this would be the Z alkene, because those two are on the same, they're cis to each other, right? So comparing the alkyne versus the hydrogen, the alkyne wins. Comparing the this acid chloride thing versus the hydrogen, the acid chloride thing wins. So priority-wise, we have our highest priority functional group, or not highest priority for naming, but higher priority atomic number for stereochemistry. So it's just if you're looking at if your higher priority groups have a cis relationship or a trans relationship to each other. So that would be the difference. Because remember, we can't rotate double bonds. So it would be stuck in one position. Okay. Awesome. Cool. So, let's see. So that was acid chlorides. What do we still have left to do? Amides. Here's our favorite solvent. This is DMF, but its real name would be N,N-dimethyl formamide. So we have two methyl groups on the nitrogen, so we need to put those as if we were naming amines, and we're going to have the rest of it just named amide. So this is formamide. That's a special, it's probably more of a common name. If we wanted to be more systematic, we would say probably N,N-dimethyl methanamide. These would be the equivalent names. Formamide's more common than methanamide, but they would be equivalent. This would be kind of more common, but it is IUPAC accepted, and this is a systematic name. So it's kind of like an ester. If you have things on your nitrogen, you would name those as substituents. If you don't, then you don't have any substituents. That's great. And you would name the rest of it the same way. So if we had something like this, we're in priority 1, 3. This is now an R stereocenter. Remember, nitrogens don't thankfully have chiral centers because they rapidly invert, so we're safe there. We would say that we have on this thing, we have N-methyl, and we have 2-fluoro, and we would just need to put those in alphabetical order. Remember that, here, I'll do another one. And we'll say that we also have N-methyl and 4-methyl. So we can see how that works together. So we would say, in this case, 2R, 2-fluoro, 4N-dimethyl, and then 1, 2, 3, 4, 5. Oh wait, I actually don't know. 1, 2. We only have 4. Sorry, I was using my priority numbers as carbon numbers. That's shame on me. Okay, we have 4 carbons, so this will be butanamide. So the same thing. Here's our parent butane idea. We change that to amide. It's nice that most of these functional groups just have their functional group as their name. So that's helpful, at least a little bit. And so this is what we would end up getting for this structure. So notice we combine the methyl groups. Doesn't matter that one's on the nitrogen on the other side. Doesn't matter. We would just name these things. We don't have to have them separate like we did with the esters. Because I don't know how to count. Yep, you're right. Good point. Yes, very good. Alrighty. Are we sick of naming yet? Too bad, we still have another one. No more synthesis, only naming. This is now naming class. What was the last one? Nitriles. Oh, these are the easiest ones. Just cyano or nitrile. So, 1, 2, 3, 4, 5, 4 methyl. Nitrile. Very exciting. I don't remember if there's 2 N's in this or not. pentanitrile. This one I'll actually have to check. So let's not talk about nitriles yet, because I don't remember if this has two N's or not. Whatever. I'll just put a question mark. I'll look that up and I'll let you guys know next week. So, but we'll go with that. Remember that these will be cyano otherwise. So just check that page I gave you so you can see if these things are substituents, you can see what to name them as. So good stuff. Anhydrides is not something we've talked about because we don't typically see these because they're so reactive, but in anhydride, you would name anhydrides, you name them separately in alphabetical order. Let's see, we've got propanoic, 1, 2, 3, 4, butanoic. So butanoic, propanoic, anhydride. So you would name these as acids, like if we had something like methyl butanoic acid or something, we would still keep everything except the word acid. So we keep everything but the word acid here, and then we just throw the word anhydride at the end. And this is done alphabetically. So butanoic, propanoic, anhydride. If you have it symmetrical, in purple, because why not? This is just propanoic anhydride. Pranhydride, propanoic anhydride. So these ones are typically easier, and you don't usually see these because they're pretty reactive, so they don't really hang around very easily, and it's pretty hard to make them. So a little bit less common. Symmetrical ones are a little bit easier because you just keep them, and then you can get them to make anhydrides, but even so with that, you really only get acetic anhydrides, so yeah. Okay, so that's all of our naming stuff. Wow. Wow. Fun. So we've just covered, 6 functional groups and how to name them. And so this is thankfully the last bit of naming that we have in the entire class. So we have now all of our functional groups out there. So I can give you any molecule I feel like and have you name it. Yay. Yikes. Okay, so now that we're dead, brain dead at least, we can do some reaction stuff. So we're going to start with acid chlorides because they're the most reactive. And since Eric wants to start doing mechanisms, we're going to see that generally speaking, things are going to follow a pretty common pattern. We're going to end up kicking out a leaving group, which I'm going to just put as Z. If you end up reacting one of these things with a nucleophile, you will just kick out your leaving group and get your nucleophile there. It's very exciting. Let's take a look. We're going to start with acid halides because they're the most reactive. So we're going to see that what's going to happen if we put a nucleophile, let's say we put, here's one, OH minus, perhaps you've heard of this before. We're going to see we kick this out, we get a carboxylic acid at the end of the day. The mechanism is 2 steps. It's important that we understand this is not a concerted process. So mechanism-wise, this is equilibrium. we end up with a tetrahedral intermediate, which then will close back down and kick out a leaving group. And this is an irreversible part here because chloride is not a very good nucleophile, or rather, it's an okay nucleophile, but we don't have a leaving group anymore. So without having special reagents, we're not going to be able to put that chlorine back in there. So we will have kicked out the chloride. So notice here we have the carbonyl closing back down again. That's actually a pretty good driving force, and so we're going to kick out our leaving group. And so all of the reactions will follow this basic idea. That's it. That's all these are. Easy reactions. They all follow the same pattern. But we just have to consider if we're in basic or acidic conditions, because the mechanism will change slightly depending where we are, if we're using those as reagents. So it's otherwise same two steps for everything. Nucleophilic attack, you form this tetrahedral intermediate. Once you have the tetrahedral intermediate, it can close back down again, and you'll end up making your carbonyl again, and you'll kick out your leaving group. So for things that have leaving groups, for these we're thinking of esters, acid chlorides, anhydrides. We don't really see amides as having leaving groups. Carboxylic acids don't really have leaving groups either, but we'll see here. So this is the main pattern of how these things are going to react. But first, as always, we should think about how to make them to begin with. We have some tools already that you remember from before. How do we make carboxylic acids? How do we make these? Well, here's one way. I just did that. So you can hydrolyze an acid chloride. That'll give you a carboxylic acid. But what ways do we know previously for how to make carboxylic acids? We've got a couple of them, right? Quite a few. We can oxidize a primary alcohol or an aldehyde. You can oxidize these things to carboxylic acids. We can use those, oxidize them. Typically you want strong oxidizing agents, chromates, permanganates, that sort of thing. Strong oxidizing agents will get you to the carboxylic acid. Peroxides will do that as well. So you know how to do that. But about from an alkyne, how do we make carboxylic acids? How do we make carboxylics from alkynes? Do we remember the reagents? Way back when. Remember, ozonolysis of alkynes will give you carboxylic acids. If you do ozonolysis using DMS as your reducing agent of alkenes, you get aldehydes, right? If they're terminal. Alkynes, they'll give you carboxylic acids. What about these things? Alkenes. How do we get carboxylic acids from alkenes? Oxidative cleavage, right? Nice, strong KMNO4 will give us carboxylic acids. If you have a disubstituted alkene, you can get carboxylic acids there. What else did we learn? Did you talk about vineyards with carbon dioxide back in 105? Maybe, maybe not. Yeah. Yep, yep. So, if you use CO2 as your reagent, yeah, you can get if you use carbon dioxide with a Grignard reagent, you will end up making a carboxylic acid. Yeah, so that's another way to do it. So lots of fun ways. You can also hydrolyze esters. I think maybe you talked about that. You'd get an alcohol as well, but whatever your other R group is, you would end up getting that. So we have quite a few ways to make carboxylic acids. And we're going to see that the kind of best thing to do with them is to make them more reactive. So all these ways to make carboxylic acids, but these are relatively unreactive. So in order to actually do anything, in order to actually react these things, we typically will convert them to alcohol to acid chlorides. And this is done using thionyl chloride. Socyl 2 will give you your acid halide. So that's this thing, this thionyl chloride. If I remember correctly, you've used this before in reactions of alcohols, putting a chlorine where the alcohol was in the same stereochemistry. Thionyl chloride can do that. If we remember, we have seen this reagent before. You end up with the same stereochemistry as your original alcohol was. Remember that? Maybe? Probably not. Okay, well, the mechanism is the same, so we'll take a look at that. So, there's something in my eye. Okay. So, I drawn this kind of terribly. Okay. Let's draw it a little bit better. There we go. First step, we're going to have our carbonyl attack. Opens this thing up. And let's go to the right this time. All right. So we've got this bit here. So many lone pairs. And we're going to close this down and kick out one of those chlorines. Apparently I'm using purple for my reaction arrows now, so I'll just do that. So we're going to kick out a chlorine. And what's interesting here is this is actually a pretty good leaving group, as we're going to see, but we'll have a few more steps to do. Look who's come to town. It's our dear friend, the chloride ion. And so we're going to see here that this chloride ion is going to come in, and it's going to go ahead and attack our mystery, I don't know how to name this thing, oxygen sulfur thing here. So we're going down. We have a chlorine here now. We have an OH. We have O with this sulfur business. Right, so here we go. What's going to happen next is we have this lovely leaving group here. We're going to have another one of our dear chlorides come around. Oh wait, why did I have this attack nucleophilically? Oh no, that was the point, that was the point. I'm sorry, I did this step too early. I need to, I'm sorry, I did this step too early. I was thinking this doesn't make sense. Sorry, we have to deprotonate first. And then we're going to attack. Sorry about that. So first we deprotonate. You end up with the same thing. Sorry. Cl comes in here. There we go. There we go. Much better. Okay. Keep this for now as was. This guy actually closes down, and that's when we're going to pop things around. Why did I open that up? Wait, we totally lost that chlorine. What am I saying? I'm sorry, I drew 2 steps there. That's what's going on. I'm sorry. This closes down, kicks out the chlorine. Yes, there we go. And then the chlorine comes and takes the H. Sorry, I was drawing like 3 steps there at once and not in the right order. So we'll move this one over for right now. So that should be the carbox, that should have that there. We're going to have our chloride now come in. Sorry, I will slow down and draw this thing correctly. Okay, there we go. We're in the correct state here. So now we can have our chlorine come take out this proton. Hooray, there we go. And now we can do some rearrangement. We get finally this thing. Now we can have our chlorine attack. Opens this up. Could have had it attack the other time, doesn't really matter. And once we do that, we have another tetrahedral intermediate. And believe it or not, this sulfur business is actually a better leaving group than the chloride is. And finally, this thing closes down. And we end up losing that bit there. So we finally end up with terribly drawn hooray. We've done it. So first step, we attack our reagent, kick out one of the chlorines. Chlorine comes, grabs a proton, we can go ahead and close this ring down, attack with chlorine again, close down the ring, kick out the O-sulfur bit, and we'll end up with our happy reagent. If we react with the OH instead, it's a little bit faster of a mechanism, but either one will work here because this thing is in resonance with itself. So, ta-da! We end up with our happy acid chloride. All right, and apparently we're out of time, but we'll see all the fun things we're going to do with that next time. All right, so that's kind of where we'll leave it off today. All right, fun stuff. All right, cool. I'll see you guys on Monday then. I'll try and have the exams graded this weekend, but we'll see. All right, cool. Take care.